So for the lab, how are you going to learn from how did you get, or what are you going to learn from the data? I moved the lab data to class view. Why did I move it to class view? So no one can change it or screw things up. You can still see it, but you can't change it. So here is the osmosis. Now remember, down at the bottom it says 4C baggies, 4D potatoes. Ignore. Ignore the ignore. Okay? You don't have to worry about that tab. Someone's going to say, but Miss Fair, I couldn't read the tab. Okay, so what were the different percentages, different solute potential, or not solute potential, solute concentrations that were in those unknown solutions in the back of the room? There is a 0, there's a 0.2, 0.4, 0.6, 0.8, and 1.0. What did you do with those baggies? And we're looking at the baggies right now. What did you do with the baggies? You put them in what? In distilled water. So, how can you figure out which solution is which? What do you mean? So? Okay, so what can we assume to be the 0 molarity solution? Why?
Because there shouldn't be a lot of changes in our system.
It had the least change. Now, should it have been 0? Yes. What does this tell me? We had error. Either you masked the bags wrong, you didn't dry them before and after, you contaminated the solutions, a whole bunch of other reasons. Does this make sense, why I'm saying this? So what can you assume is the 0.2?
The purple.
The purple. What about 0.4? 0.8, and so on, or so on and so forth. Make sense? Now, how are you going to graph this data? Bar graph. So here's my bar graph. How am I going to set this up?
The colors go on.
No, not the colors.
I meant the molarity.
The molarities. I want to put it as 0, 0.2, 0.4, 0.6, 0.8, 1.0 percent change in mass. Right? Yes or no? Now, I would, because I'm anal retentive and I always want to make sure I get as much information as I can, I would put a mark here that says this is the dark blue black. That way, when I get to the next graph, when I next get to the next information, it makes sense. Does that make sense?
How can you do that on the, like, what's the setting thing? You just add a text.
Yeah, you just add a text box to it.
Okay.
You can also hand draw these graphs. Okay, so questions there. Does it make sense which molarity is which vial? Yes? Okay, so now, once you know this, now we can figure out the molarity of the potato. Oops. So if I look at my molarity of the potato, once again, I had my 0, my 0.2, my 0.4, my 0.6. What did I do with my potato? Someone.
You put it in
No
there.
one in here did this lab.
You waited before and then put it in there and then
Waited before, put in the different solution, waited after. So what can I assume? What do I already know? I already know that purple, no, dark purple was 0 molarity. What happened in 0 molarity? What happened to the potato? It, don't say absorb. It gained 10% mass. Why did it gain 10% mass? Because the environment was hypotonic to the hyper potato. Right? Yes or no?
Yeah.
So what I would do is I'd graph these out. I'd first of all keep the same order as I had before. 0, 0.2, 0.4, 0.6, 0.8. But I'm going to add an extension line to my graph. Why am I adding a down line? Because there's negative. So 0, it gained. 0.2, what do you think? Did 0.2 gain or lose?
Which one?
What do you think?
We don't know which one is.
You actually can tell from this data.
Oh.
But I can go back. Okay, so which one is 0.2? Purple. So did purple gain or lose?
Still gain.
Gain, but less. Now the rest are losses, right? Something like that. So how do I determine my molarity of my potato? Denise?
Oh, I just said it's probably somewhere between 0.2 and 0.4.
Somewhere between 0.2 and 0.4. So I make a line of best fit, and my graph says it's about 0.3. Does this make sense? Now, your numbers may be different from mine. Don't just copy this down, because that would be a 0. You can graph it, you can determine your line of best fit, wherever it crosses 0. Why would that be the molarity of the potato?
Because it's not changing its weight, which means it was isotonic.
It was isotonic to the environment. Does that make sense? Yes?
So do we graph average
Okay.
values and
Now, in the directions, you need to graph your data as compared to class average. No. How many graphs would you have? You still have 2 graphs. One for 4C, one for 4D.
we just add on here?
You're going to have a double bar graph.
Except only for the 2 that we tested. The 2 solutions.
Correct. Now, why do I want you to do that? Because if I remember right, no, it was third group. There was one group that they brought me their numbers, and I'm like, I don't know what the hell you did wrong. Because they had a negative 53, which should have been a positive. I'm like, seriously, no. And so I did not add their data into the chart. Does that make sense? Yeah? Yes? Okay. So, lab is due next class. I don't want to hear anyone come in on Monday, but I didn't understand it. That's why you have tomorrow to check in with me. You also need to read, instead of chapter 7, no, chapter 6 was due today.
Oh.
Instead of chapter 7 next class, I'm actually switching the order, going to go to 32.3, 32.4. Because we're going to talk about excretory system and how it relates to osmosis. You might want to write that down. Unless if you get reminded after where I sent it out during lunch.
And then blackboard quiz.
The Blackboard quiz needs to be done by 8 o'clock on Sunday night. Why am I saying 8 o'clock on Sunday night? So at 7:55, if you have a problem, you'll be able to contact me and I'll be able to reset it. At 7:55, I'm going to laugh because there's no way you can finish it. But, know, this is trying to get you guys to realize that doing things a little earlier is probably better than waiting to the very last second. It helps?
Yeah.
It helps? Oh my gosh.
I'm not doing the quiz at like 10:30.
Yeah, and you probably are a little bit more fresh in the mind. Well, okay, then there's you. Okay, questions here. Questions.
Yeah, so for E and for F,
What?
the calculations and stuff.
I just did it. That was the quiz. So now you should be able to go back and do that. And if not, be here tomorrow.
And then for the pre-lab,
Guys, please.
each field is a part of the pre-lab asks for safety considerations. Can we just do one big one for the entire pre-lab?
That's fine.
Because I just like copy.
Yeah.
So for the fun stuff, we do what we do sometimes, and then it's graphs.
If you go onto the original Google document, it actually outlines there what you need to do. Yes.
So for the title, like, since there's like 6 parts, does the title like summarize everything?
Osmosis, diffusion, Brandon is annoying. Any of those titles are acceptable. Miss Fair is the best person in the world.
Did you ever figure out that question thing, or was the question like 1, 2, 3 or whatever?
Yeah. So, okay. So, guys, on Google Docs, I actually went back and I changed the original, saying questions from the half sheet. The half sheet is not last class.
Wait, it just what?
Oh, yours was a full sheet. Some people got full sheets, some people got half sheets.
No, we can
Okay.
see every Google Docs stuff.
So this is what we're going by, not
That, and you have to look at the Google Docs to tell you what you're going to graph.
Okay. So this doesn't say like, let's say for A, it doesn't ask for like error analysis. It says
If you look at the Google Docs, and if you look at that, it says it right there. Okay, questions?
sorry. We were talking about.
Guys, stop!
So we were talking about, you just discussed how you do data for like transfer. You would just be like, you subtract this from this, and then you square this, but you're not actually doing it.
You don't have the known data.
Or like if you're doing like standard deviation.
Yeah, but you don't have the known data, so you're not going to do any calculations. You're going to describe what is the best method to use. Okay. I have no idea off the top of my head. Okay, questions. Okay, we are going to hit energy exchanges. This is the notes for today. Everything else is a must-know. Again, guys, those of you who are just taking these must-knows and just putting them away, that's not the best plan. Because some people discovered that the same questions that were on the must-know were on the quiz today. So had you gone through those steps, it would have been easier. Oh wait, that's expecting you guys to. Well, I strongly advise to do it. So yeah, the water potential. I'm not going to collect it because those of you who did it better. Probably will do better on the quiz.
The notes that we started with,
What notes?
Oh yeah.
Yeah, we finished them. And if not, they're on Google. They're on YouTube. My videotape of them. Okay. So, today we're going to talk about energy exchanges. So, this is going to bring back horrible, painful memories of AP Chem and Chem.
On the left, it
Um,
becomes
if you are having PTSD moments and you need to run out of the room screaming, that's fine.
you
Okay.
okay. But that's so.
It really is good.
So some of the things I'm going to talk about, you're going to be like, oh my gosh! Just deal. Okay, so the laws of thermodynamics. What is the first law of thermodynamics?
Energy cannot be created or destroyed.
Energy cannot be created or destroyed. Energy can be transformed. What's the way that energy is transformed? Okay, potential to kinetic. Chemical to electrical. Okay, good. What about, think back to ecology. Beginning of the food web.
Isn't it that little pyramid thing?
Okay.
And it loses like 10% issues.
Okay. So the food pyramid, as you go up the food pyramid, you're losing energy. That's going to go to the second law of thermodynamics. But we're going to take the sun's energy and change it into chemical energy. Right? So we're transforming it. Now the second law is all exchanges, all energy exchanges lead towards entropy. Whoa, did I spell that wrong? So what the heck is entropy?
Disorder. Random disorder.
Chaos.
I call this entropy.
Oh,
Yeah.
It's a
Look
red
at
flag.
RJ's notebook. That is entropy. Disorder, chaos. So as we go up the food chain, we're losing so much energy. What did we teach you freshman year? How much energy was passed on? That's a lie!
Is it like
It's somewhere between, I think it's like 17 and 25%. No, 7 and 25, something like that. No, why do we say 10%?
It's easy.
It's easy. If you go 1,000 joules at the bottom level, then we have 100 joules, then we have 10 joules, and we have 9 joules, or 1 joule. Then we have no joules, and then you're very sad.
Oh, I get it. Haha.
Jewels, Jewel, gems,
Come on, guys.
jewelry.
Come on. Let's get together.
Come on. Okay. So whenever energy is transformed, some energy is lost. So energy is lost as heat. It's a cold wintry day. What does your mom say?
Put on a jacket.
Put on a jacket, put on a hat, put on gloves. Why?
So your body warm.
So you don't get sick. That's not the reason.
Keep your body warm.
Keep your body warm. Why do you want to keep your body warm? To not die. Okay, if your body temperature is too cold, it's going to be easier for viruses and bacteria to infect you. Because your kinetic energy is slowing down. So your white blood cells are going to slow down.
Oh.
Connecting knowledge.
Kind of crazy.
How does this connect to enzymes?
They speed up.
Enzymes slow down in the cold. Oh my god.
Enzymes they're not going to slow down, but the enzyme reactions will slow down in the cold.
Let's all say it together.
Oh, what's the difference between entropy and enthalpy?
Enthalpy is the heat of the reaction. Entropy is disorder.
That's right.
I don't even know what that means.
We'll talk about that.
Delta.
We'll go through that. So, order is maintained by constant free energy input into the system. So, if we're constantly losing energy, how do we have life on Earth? Energy is maintained by input of energy. Life is maintained by input of energy. Where is that input of energy ultimately from?
Food.
Oh crap.
Just I swear I told you I don't know.
Thank you. The sun. I'm going to ignore this. I'm going to put a plastic box over this.
That's my life.
So, the increase of disorder is offset or balanced by biological processes that maintain order, that cause order. So, increase of disorder, increase of entropy, is offset by the biological processes that increase the order. Increased disorder is a bad thing. We don't want increased disorder. So our biological processes try to balance things out.
But I thought, like, we were always moving towards more disorder.
But as an organism ourselves,
Bless you.
we don't want disorder. As an organism myself, I always want to maintain homeostasis. In comparison to my environment, I'm moving towards disorder. Obviously. More ways than one. So this is where your question came in. So are we actually violating the second law? As an organism ourselves? No. Or sorry, as an organism ourselves? Yes. As compared to the system? No. So we say, so yes, at the organismal level, but at the system level, at the ecological level, we're not. Just like we never talked about evolution as occurring in one species, one individual, I can't say Lauren is more evolved than anyone else. I could say the human species has evolved, right? Some of you are less evolved than most of you, than the rest of you. I.e. this first table up here. Oh. Okay, so energy exchanges. Okay, I'm sorry. This is where the PTSD might hit you. Okay? I have to, I'm sorry. I actually texted Miss Neer telling her about the PTSD episodes in third period.
What'd she say?
Oh, I missed. She's like,
That's delta, not an A. Okay, so delta H is the change in enthalpy. Enthalpy is the heat of the reaction. Delta G. So the change in enthalpy equals, I hate saying this one because it's the one you guys get mad at. Gibbs free energy plus temperature in Kelvin. Whoops. I'm going to call this whole thing energy loss to the system. Which is temperature in Kelvin times delta S, which is the change in entropy. So delta H is the change in enthalpy. That's the energy lost or gained. That's the total energy. Gibbs free energy is the energy allowed for a reaction. Energy available for a reaction. Plus energy lost to the system, which is temperature in Kelvin, times the change in entropy. So what does this formula mean in English? Because this is all biology here. During every energy exchange, some energy is available for work, and some is lost to the environment. For every energy exchange, some energy is available for work, some energy is lost to the environment. Or gained from the environment, either way. So that can be positive or negative. Okay. Does that make sense? Yes or no? No screaming yet? Okay, now this graph doesn't look familiar at all, right? Right? We dealt with it with enzymes. Enzymes lower the activation energy. So this is the energy required. Remember this? This is the activation energy. The energy required for a reaction. This is the energy released. So this is actually delta G. Delta G is the change in energy. Delta G is the change in energy. The activation energy is the energy required to make a reaction go through. What do enzymes do? They lower the activation energy. So these are my reactants. These are my products. This is where it's a slight change from chem and AP Chem. We call this type of reaction exergonic. AP Chem, I think you called it exothermic. Tell me something about an exergonic or exothermic reaction. Heat goes out. So energy is released. What else? I don't want to say bonds form or bonds break because both of these do both. So this is when we go from unstable molecules to stable. So if you think about it, glucose is actually not really a stable molecule. We want to break down glucose. Glucose wants to be broken down, right? So it's going from unstable to stable. Make sense? No? Excellent. It's going from more ordered to less ordered. How does that relate to entropy? More disorders appearing, right? It's a downhill reaction. You can see that, right? Yes. My delta G is negative. You can do that mathematically. What's the key thing here, though? Do I have to put in energy to make the reaction occur? In the long run? No. It's a spontaneous reaction. This is a spontaneous reaction, which means cellular respiration would occur on its own without enzymes. It just would be slower. Enzymes speed it up. Make sense? Yes or no? So, what are some reactions in the human body that would be this process? That there's a release in energy. Cellular respiration. Cellular respiration. There's a prime example of an exergonic reaction. When else? Sort of related to cellular respiration. You're probably doing it right now after lunch. Digestion. How is digestion an exergonic reaction? You're breaking down molecules, and when you're breaking them down, you're releasing heat. Does that make sense? No. So is it good to eat when you're cold? It's not going to heat your body. Oh, goodness gracious. Okay, now here's an example of an endergonic. You probably learned this as endothermic.
Why is it used for me?
Because thermic is talking about chemical reactions. This is talking about human, like organismal bodies.
Oh.
Reactants, products. This is my delta G. My delta G is positive here. This is an uphill reaction. This is non-spontaneous. Because we have to input energy to get it done. So this one goes less ordered to more ordered. Why would that be endothermic or endergonic? Less ordered to more ordered.
It's against the second law.
Well, it's going against the second law, right? We're not going towards entropy, we're going away from entropy. Right? It's going from stable molecules to unstable. That part always gets me. Why would this be endergonic? I don't know why, but this part always confuses me. Why would that be endergonic? Why would stable to unstable be endergonic? Because when you're stable, you're balanced, right? It's going to require energy to get us off balance.
But isn't that less ordered?
But the molecules. Okay, so CO2 and H2O are more stable than glucose. Glucose is less stable. Less order to more order, as in, that's talking about more of the system itself. Less, because we're causing us to go away from entropy. Okay, so delta G is positive. I said that. Common example, photosynthesis. What else would be an example in the human body? Photosynthesis is taking CO2, H2O, plus light makes glucose and oxygen. How many of you remember that formula? All of you should. Brandon, what do you think? Digestion is breaking things down. Building muscles. Building muscles. So polymerization. Fancy term. Now, I have to ask this review question because I'm evil and, well, I'm evil. If using water, what would I call it? Oh my god. Third period. It got it right out. No one said hydrolysis. Dehydration, synthesis. You actually go home. Miss Fair lost it on a student. You're right. Also known as condensation. Pooja, you said a certain type of steroid. Anabolic. I'm not reviewing here, am I? All that's brand new, right?
Yeah.
Right?
Yeah.
So, if I go back, what could I add here? Hydrolysis. What else? Catabolic. Remember, my cat tears things apart.
It's really cute. I'm allergic, but I think it's
Okay.
I can do
So, once again, we're going to talk about, do living organisms, are we violating the second law? Are we always going towards entropy? No. What we're doing is we're coupling reactions. Order is maintained.
What chapter of the textbook is this?
What you read last night, chapter 6. Order is maintained by coupling ender
I was asking for more.
and exergonic reactions. What do I mean by that?
They work
Both of
together.
them.
The storage of energy from endergonic
Powers.
powers the exergonic. The release of energy from exergonic powers the endergonic. We use them together as a cycle. We like cycles. Cycles are good. So here is a good diagram of coupled reactions. The purple line is what? Ender or exer? Exergonic. Here's endergonic. So in the human body, let's talk about a human because we like humans. Well, there are certain humans I don't like. If that doesn't surprise anyone. So, in a human, what's an exergonic reaction that's going to happen in you?
Digestion.
Digestion. So, digestion. I'll use this example first. So, digestion, you are right now digesting polysaccharides, polypeptides, lipids, nucleic acids. Am I right? You have no idea what I'm talking about. Yes! So, you are digesting all these molecules. So, a polysaccharide. Right? What happens when you digest them?
Just kidding.
You're breaking them down into the monos. Right? What else happens there? What do we have to... How does that deal with water?
It doesn't.
Monosaccharides. The monosaccharides are going to be what? Your sugars. Okay, and so your monosaccharides will be used to go through cellular respiration. Cellular respiration releases what? ATP. Cellular respiration releases ATP. What's that ATP going to be used for?
Endergonic.
Endergonic reactions, building muscle, which I'm missing.
Wow.
So this is going to power my endergonic reactions to build my muscle. Polymerization. None of you can photosynthesize, I'm sorry to tell you. Does this make sense what I'm saying here? Now, so this energy that's being released from exergonic reaction powers the endergonic. Uh-oh. How does endergonic relate to exergonic? When we break down those polymers, when we do other processes. What's another example of polymerization? Using a tRNA and an mRNA and an rRNA. Transcription and protein synthesis. So protein synthesis as well. So these endergonic reactions are then going to store energy that we can use for exergonic, or make the molecules for the exergonic. Do you see how we're relating things? I was dancing. You should have given me a break. Okay, so the endergonic reactions are making those macromolecules, right, that we're going to use to break down for exergonic reactions, which is why you can survive for a couple weeks. If you're not eating food, you can still survive. Yeah, it's a cycle. Okay, ATP is adenosine triphosphate. What macromolecule is ATP? It's ATP. That's not a macromolecule. What are the four macromolecules?
The protein.
Protein, lipid, carbohydrates, nucleic acids. Fats are lipids. Which one is ATP? Nucleic acid. If it's a nucleic acid, what is it? What is the monomer? Nucleotide. What are the three parts to nucleotide? Nitrogenous base, a sugar, and at least one phosphate group. So here's an example of ATP. Adenosine. This is my ribose sugar. And these are my three phosphate groups. These are weak bonds, weak covalent bonds. So think back to freshman year. I know it's a long time ago. Some of you it was just like yesterday. So, when I break down ATP and I release a phosphate, what do I make? ADP. This is going to be my P1, my P2. What do you think this is?
P3.
P10. I almost wrote 4 there. I will admit. So, we break this off and we make ADP. If we break this off, I'm going to make a connecting knowledge here. If we break both of those two off, then we add a cyclic molecule. Cyclic AMP. When do you see cyclic AMP? Right before the phosphorylation cascade? What enzyme does that?
Just kidding.
Well, it's using a G protein. That's the adenyl cyclase.
Protein kinase.
Adenyl cyclase. Remember, the G protein triggers the adenyl cyclase to make the CM.
Right.
Okay. Now, I'm gonna have to do this because this is good time to review here. So the G protein, what powers that G protein to shoot on over? The ligand bond, but it triggers something to act. Phosphate. phosphate group to what?
Make it exciting.
Why is it called a GTP? I just gave you the answer. Dang it. Why are they called a G protein? Because they use GDP and GTP. Does that sound familiar? So instead of ATP, we have guanine here.
Oh, that makes sense.
There's also what's known as TPP, thymine.
Wait. Oh my god, wait a second.
Oh my God. What do you think there's also going to be?
Uracil.
There are different forms of those nucleic acids. They're all used for energy. We'll talk about that when we get to DNA replication. We haven't done DNA replication yet. Oh dear God, we still have more.
Wait, so the little two things boxed up, what does that represent again?
I like it.
Oh, that's when the two phosphates come off and it makes that C amp.
Okay.
What?
You said when we cut off the one phosphate.
It becomes ADP, adenosine diphosphate. If I break off two, it becomes CAMP. Okay, so we have, this is left. This is it. We can get through this. I promise you. We will not explode. If your PTSD hasn't hit yet, you're fine. So, this is my exergonic reaction. My exergonic reaction does what? Releases ATP, releases energy. This powers my endergonic. My endergonic is going to power the ADP plus a phosphate. Do you remember when we talked about ATP loses a phosphate, ADP gains a phosphate? This is the pattern here. So endergonic forms the ADP, we add the phosphate group, and now we have the energy for exergonic. And around, and around, and around, and around until you die. By the way, when you no longer gain energy, you're dead. Okay, I don't want to talk about this. I do. Mechanical versus transport versus chemical. Tell me an example of each.
Operate.
I don't care.
Transport. No, that can't be.
Full sentence.
I think I messed up. I see them. I did a chart in my mind.
Read it.
Excellent. Thank you. Okay, mechanical. That can be movement.
Oh,
That's beating of cilia, beating of flagella, beating of pili. If those words don't sound familiar, you might want to review.
Movement.
Muscular movement, actin, myosin, microtubules. Do any of these words ringing a bell?
No.
You may not know what they mean, but you at least have heard of them, right? Transport could be facilitated diffusion, could be active transport. What's the difference between facilitated diffusion and active transport? By the way, this is this unit, so you should know this. Active transport is going against the current. Facilitated diffusion is you going out the door right now.
Can't wait.
I know. The pumps are all the transport. Sodium, potassium pumps. Chemical, that's going to be the endergonic reaction. That's going to be the polymerization. That's going to be the protein synthesis, DNA replication, those things. Wow. One more. Okay, so what do we use our free energy for? There's two body plans, temperature plans organisms have. What are the two main temperature plans organisms can have? Temperature, maintaining temperature. Endothermy or ectothermy? Endotherms versus ectotherms. Ectotherms really are not a good term for it. It really should be called poikilothermic. Should have known that. Yeah, you should have known that. Ectothermic, that just means that the temperature is the exact same as the environment. It's not really. Poikilothermic means that they can't moderate their body temperature. We shiver, we sweat, we try to maintain our body temperature, right? How is that going to require more energy?
You have to go against it.
Because you have to go against what's natural. You're in a cold environment. You have to shiver. Reproduction. When a female is pregnant, she has to ingest 1.2 times the amount of food. Not 2 times the amount of food. When I was pregnant, my doctor's like, you do realize you're not eating for 2, you're eating for 1.2. And I'm like, no. The larger the organism, the slower the metabolic rate. Did you guys know that dogs, small tiny dogs, have a really fast heartbeat? But larger dogs get slower. Elephants, very slow heartbeat. Hummingbirds, very fast.
Yeah.
Because they don't have to search for food. They don't have to respond. If you don't have enough energy, you lose mass, i.e. you diet, or you die.
That's why you don't die.
That's why you don't diet. Yes. Okay. Done.
I like what happens on TV.
Okay, ladies and gentlemen, make sure you read. I'm wondering if I should have a reading quiz. Should I have a reading quiz?
No, we're having a reading quiz.
I don't know. Maybe. What's a reading quiz? Basically asks, can you read? Yes, it'll be in Spanish.